Welcome! Today, we'll be diving into LeetCode problem number 306, additive number. This is an interesting string-based problem where we determine if a given sequence can represent an additive series of numbers. We'll explore various approaches to solve this and discuss the challenges involved. Let's get started. An additive number is a string of digits that can form a specific type of sequence, called an additive sequence. This means that starting with the first two numbers in the sequence, every subsequent number is the sum of the two numbers immediately before it. For example, if the first two numbers are 1 and 1, their sum is 2, which becomes the next number. Then, 1 and 2 sum to 3, and this process continues. Once the first two numbers are chosen, the rest of the sequence is uniquely determined. Importantly, for a string to represent an additive sequence, it must include at least 3 numbers, and numbers in the sequence cannot start with leading zeros, unless the number itself is 0. Given a string number consisting of digits, your task is to determine if it is an additive number. If it is, return true, otherwise, return false. Let's look at an example to understand this better. Consider the input string number equals 112358. The output is true because this string represents the sequence 1, 1, 2, 3, 5, 8, which is a valid additive sequence. To verify, we check the sums 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and 3 plus 5 equals 8. Each number in the sequence is formed by adding the two numbers immediately before it. This satisfies the conditions of an additive sequence, so the function should return true. Now, take the input string number equals 199100199. The output is again true because this string can represent the sequence 1, 99, 100, 199. Let's validate it step by step. First, 1 plus 99 equals 100. Then, 99 plus 100 equals 199. Since every number in the sequence follows the rule of being the sum of the prior two, it qualifies as an additive sequence. Therefore, the result is true. Another example is number equals 123, which represents the sequence 1, 2, 3. Here, 1 plus 2 equals 3, satisfying the additive rule, so the output is also true. However, not all strings will form valid additive sequences. Take the input 1023. In this case, no matter how you split the string, it's impossible to create a sequence where each number is the sum of the previous two. For example, if you split it as 1, 0, and 23, the sum of 1 and 0 does not equal 23. Similarly, any other splitting fails to meet the additive criteria. Therefore, the output for this input is false. Let's now discuss the constraints and edge cases. The input string will have a length between 1 and 35 characters and will only contain numeric digits. For short strings with fewer than 3 characters, such as 12, it's obvious that they cannot form an additive sequence because there aren't enough numbers to satisfy the additive condition. Strings with leading zeros, like 1023 or 1203, are also invalid because numbers in the sequence cannot have leading zeros unless the number itself is 0. Lastly, for longer strings near the upper limit of 35 digits, we must ensure our solution handles them efficiently, even when the sequence is valid. Finally, let's consider some edge cases involving repeated digits. For example, the string 000 is a valid additive sequence because 0 plus 0 equals 0. This shows that even sequences with repeated digits can satisfy the additive property as long as the rules are followed. By keeping these edge cases in mind, we can ensure our solution is robust and handles all possible inputs. To solve the additive number problem, the main challenge lies in splitting the given string into valid numbers that satisfy the additive sequence property. One approach we considered is the brute force method, which is straightforward and involves trying every possible way to split the string into the first two numbers. From there, we simulate the sequence by calculating the third number as their sum and checking if the string can be fully reconstructed by repeatedly applying this logic. While this method is easy to implement and follows a clear, logical flow, it comes with significant trade-offs. The time complexity is cubic, n cubed, because we iterate over all potential splits and validate each sequence, which becomes inefficient for longer strings. Additionally, we must handle edge cases like leading zeros to ensure correctness. This approach is simple but not ideal for large inputs due to its inefficiency. An alternative method we explored is optimized backtracking. Here, the goal is to systematically explore potential splits while avoiding unnecessary computations, especially when a split is invalid early in the process. Using recursion with backtracking, we can check if each split satisfies the additive property before proceeding further. If a valid sequence is identified, we continue recursively to verify the rest of the string. This approach introduces a more structured way of exploring the problem, and it avoids redundancies inherent in brute force. However, the time complexity remains O(n) cubed, because we still evaluate all possible splits, and the space complexity increases to O(n) due to the recursion depth. While this method is more organized, it does not significantly improve efficiency and introduces additional overhead from recursion. We also considered an optimized iterative simulation approach, which eliminates recursion and focuses on minimizing checks while simulating the sequence. Using nested loops, we pick the first two numbers and iteratively compute the rest of the sequence, verifying the additive property at every step. This method improves efficiency by reducing the time complexity to O(n squared, as it avoids the repeated overhead of recursion. Furthermore, its space complexity is constant, O(1), since no additional memory is required for recursion stacks. However, this approach requires meticulous handling of edge cases, such as leading zeros in very long strings. Despite these challenges, its efficiency and simplicity make it a cleaner and faster solution compared to both brute force and backtracking. After evaluating the approaches, we chose the iterative simulation method as the most practical solution. The brute force method served as a helpful starting point due to its simplicity, but its inefficiency made it unsuitable for larger inputs. Optimized backtracking, while more structured, still retained cubic time complexity and introduced additional space requirements. The iterative simulation approach stood out because it balances clarity and efficiency, reducing the time complexity to O(n squared, and avoiding the overhead of recursion. By combining the splitting and validation steps into a single iterative process, we achieved a streamlined method that is faster and easier to implement. Key considerations include handling leading zeros and efficiently validating numbers to ensure correctness. This approach provides the best trade-off between speed, clarity, and practicality. Every approach has its trade-offs. The iterative simulation method is highly efficient but comes with the challenge of carefully addressing edge cases, such as leading zeros in very long strings. On the other hand, backtracking, while more intuitive and systematic, incurs higher space and time costs, which limits its scalability. The brute force approach, though conceptually simple, is impractical for larger inputs due to its cubic complexity. In choosing the iterative simulation method, we prioritized efficiency and clarity, ensuring a solution that can handle a variety of scenarios without excessive computational overhead. This makes it the most effective strategy for solving the additive number problem. To determine if a given string represents an additive number, we can follow a systematic brute force approach. First, it's important to understand what an additive sequence is. In such a sequence, every number from the third onward is the sum of the previous two numbers. For instance, in the sequence 1 1 2 3 5 8, you can see that 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and so on. Now, since the input is a string of digits, our goal is to split it into at least 3 parts, ensuring that the first two numbers lead to the subsequent numbers following the additive property. To achieve this, we need to iterate over all possible lengths for the first two numbers. Using two nested loops, we can systematically explore all valid combinations of lengths for the first and second numbers, denoted as len1 and len2. While iterating, we also verify that the remaining portion of the string is long enough to form a valid sequence. These initial steps help us establish a framework for testing potential additive sequences. Once we have determined the lengths of the first two numbers, the next step is to extract the actual numbers from the string and validate them. For each combination of len1 and len2, we extract the first two numbers. It's crucial here to ensure that these numbers do not have leading zeros, as such numbers are considered invalid unless the number is exactly 0. After validating the numbers, we simulate the additive sequence. Starting with the first two numbers, we repeatedly calculate their sum and check if it matches the corresponding substring in the string. If we can consume the entire string while maintaining the additive property, then the string represents a valid additive number. Additionally, we handle edge cases, such as strings with fewer than 3 characters, which are immediately invalid because there aren't enough numbers to form a sequence. Leading zeros in the input are another edge case that must be handled carefully to avoid invalid splits. Finally, if no valid sequence is found after testing all possible splits, we return false to indicate that the string is not an additive number. This approach relies on several key insights to make the brute force exploration efficient. First, by systematically testing all possible splits of the string into 2 initial numbers, we ensure that no potential combination is missed. The condition that numbers cannot have leading zeros, except for the number 0 itself, is critical for validating the extracted numbers. Another important insight is that instead of converting the entire string into numbers up front and validating the sequence, we construct the additive sequence step by step by checking substrings of the string. This avoids unnecessary computations and ensures that we are verifying the sequence incrementally. Finally, we can optimize the process by pruning invalid cases early. For instance, if the remaining portion of the string after selecting the first 2 numbers is too short to form a valid additive sequence, we can skip further processing for that split entirely. These insights help refine the brute force approach and make it practical for a problem of this nature. To implement this algorithm effectively, we rely on specific data structures and techniques. String slicing is a key operation, as it allows us to extract potential numbers from the string using indices determined by len1 and len2. This makes it easy to dynamically test different splits. Additionally, 2 pointers are used to track the start and end of the current substring being processed. This simplifies traversal and ensures that we can efficiently validate substrings. Another important aspect is dynamic number construction. By converting substrings to integers on the fly, we validate the numbers as they are constructed, ensuring that they meet the criteria for a valid additive sequence. Together, these techniques provide the foundational tools needed to efficiently implement and test the brute force solution. The algorithm also involves several core operations that are critical for validating an additive sequence. Substring matching is one of these operations. When we compute the sum of 2 numbers, we check whether the resulting value matches the next part of the string. This ensures that the sequence adheres to the additive property. Another important operation is the conversion of string substrings to integers, which includes validation to ensure there are no invalid leading zeros. This step is vital for avoiding splits that do not represent valid numbers. Finally, the nested loops used for exploring all possible splits incorporate an iterative and backtracking process. When a particular split fails to satisfy the additive property, we backtrack and try the next potential split. This systematic exploration ensures that all possible sequences are considered without prematurely discarding valid ones. When analyzing the complexity of this algorithm, we observe that the time complexity is O(n cubed). This arises from the 2 nested loops that determine the lengths of the first 2 numbers, which result in O(n squared) iterations. For each split, we then validate the sequence by iterating through the rest of the string, leading to an additional factor of O(n). As a result, the overall time complexity is cubic in relation to the length of the string. On the other hand, the space complexity is O(1). This is because we use only simple variables for indexing and validating numbers, and no additional data structures are required. By keeping the space usage minimal, the algorithm focuses entirely on processing the input string efficiently while systematically exploring all possible additive sequences. Here, we begin by defining a class called solution and implementing the isAdditive number method, which takes a string number as input. The length of the string is stored in n. Inside this method, we define a helper function called is_valid_sequence. This function helps us verify if a sequence starting from given numbers forms a valid additive sequence. It takes 3 arguments, the first and second numbers in the sequence, and the current starting index in the string. In the loop, we calculate the next number in the sequence by adding first and second. This result is converted to a string, and then we check if the substring starting at the current index matches this calculated number. If it doesn't match, we return false. Otherwise, we update the start pointer by advancing it by the length of the next number, and shift first and second forward in the sequence. If the loop completes without issues, the function returns true, indicating that the sequence is valid. Below this, we use nested loops to try all possible pairs of first and second numbers by splitting the string at different indices. For each pair, we extract the substrings representing these numbers. We first check if either of the two substrings has leading zeros, as numbers with leading zeros are invalid. This is done using a simple condition: if the length of a substring is greater than 1 and it starts with 0, we skip the current iteration. Next, we convert the valid substrings into integers, assigning them to first and second. With these numbers, we call the is_valid_sequence function, passing in the current values of first, second, and the starting index of the remaining part of the string. If this function returns true, it means we've found a valid additive sequence, and we return true from the main method. If none of the pairs lead to a valid sequence after trying all possibilities, we return false, indicating that the input string is not an additive number. Here, we begin with the Java implementation inside a class named solution. The main method is isAdditiveNumber, which takes a string number as input. The goal is to determine if number is an additive number. First, we calculate the length of the string and define a helper function called isValidSequence. This function is designed to check if a sequence starting with two given numbers forms a valid additive sequence. Inside the helper function, we use a while loop to traverse the string, calculating the next number in the sequence as the sum of the first and second numbers. We then convert this sum to a string and check if the substring of number at the current position matches this calculated string. If it doesn't match, we return false, as the sequence is invalid. Otherwise, we update the pointers by shifting the start index forward and reassigning the first and second numbers, continuing the process. If we successfully validate the sequence for the entire string, we return true. Now, we attempt all possible combinations of the first and second numbers by iterating through the string using nested loops. The outer loop defines the end of the first number, while the inner loop sets the boundary for the second number. For each combination, we extract the substrings representing the first and second numbers. Before proceeding, we ensure these numbers are valid by checking for leading zeros. If a number starts with 0 and is longer than one digit, it is skipped. Next, we parse these substrings into long integers and pass them, along with the starting index of the remaining string, to the isValidSequence function. If this function returns true for any combination, we know the string is an additive number and can return true immediately. If no valid sequence is found after trying all combinations, we return false, indicating that the string does not represent an additive number. To solve the problem of determining if a number is an additive sequence, we first consider the input number equals 112358. The length of this string is 6, and the algorithm begins by trying all possible combinations of the first and second numbers. In the first iteration, we set I equals 1 and j equals 2, which correspond to the indices that separate the first and second numbers in the string. From this, we extract first_str equals 1 and second_str equals 1. These are then converted to integers as first equals 1 and second equals 1. Now, we call the helper function is_valid_sequence with these values and a starting index of 2 to validate whether this forms a valid additive sequence. The validation process begins by checking if the remaining part of the string matches the expected additive sequence. First, we calculate the next number as next_number equals first plus second equals 1 plus 1 equals 2, and convert it to a string next_number_str equals 2. Since the string starting at index 2 begins with 2, we update the values to first equals 1, second equals 2, and start equals 3. Next, we calculate next_number equals 1 plus 2 equals 3 and check if the string starting at index 3 begins with 3. It does, so we update first equals 2, second equals 3, and start equals 4. We repeat this process, finding next_number equals 2 plus 3 equals 5, which matches the string starting at index 4, and then next_number equals 3 plus 5 equals 8, which matches the string starting at index 5. At this point, the start index reaches the end of the string, confirming that this is a valid additive sequence. The function returns true for this example. In the next example, the input is number equals 199100199. Here, the string length is n equals 9, and we again try all possible combinations of the first and second numbers. For the first iteration, we set I equals 1 and j equals 3, resulting in first_str equals 1 and second_str equals 99. These are converted to integers as first equals 1 and second equals 99. The helper function is _valid_sequence is then called with these values and a starting index of 3 to validate whether the remaining string forms a valid additive sequence. For validation, we check if the rest of the string matches the expected sequence. First, we calculate next_number equals 1 plus 99 equals 100 and convert it to next_number_str equals 100. The string starting at index 3 begins with 100, so we update the values to first equals 99, second equals 100, and start equals 6. Next, we calculate next_number equals 99 plus 100 equals 199 and confirm that the string starting at index 6 begins with 199. At this point, the start index reaches the end of the string, meaning the sequence is valid. The function returns true for this example as well. In the final example, the input is number equals 123. The length of the string is n equals 3, and the algorithm attempts all possible combinations of the first and second numbers. For the first iteration, we set I equals 1 and j equals 2, which results in first_str equals 1 and second_str equals 2. These are converted to integers as first equals 1 and second equals 2. We then call is_valid_sequence with these values and a starting index of 2. During validation, we calculate next_number equals 1 plus 2 equals 3 and find that the string starting at index 2 begins with 3. Since this brings us to the end of the string, the sequence is valid, and the function returns true for this example as well. To analyze the time complexity of the solution, we start by breaking it into its main components. The first major contributor comes from the outer loops where we choose the first and second numbers of the sequence. The first loop iterates through all possible lengths of the first number, represented by I, which can range from 1 to n1. This gives us n iterations. The second loop, nested within the first, iterates through all possible lengths of the second number, represented by j. For a given I, the values of j range from I plus 1 to n, meaning the number of iterations depends on the value of I. When summing over all possible values of I, this results in about n squared iterations in the worst case. Additionally, within the helper function is _valid_sequence, we generate and validate the additive sequence by comparing substrings. For each valid pair of first and second, we may traverse the entire string number, contributing n time. These steps form the basis of the time complexity analysis. Now, let's combine the contributions to calculate the total time complexity. The outer loops produce n squared pairs I, j, and for each pair, the helper function validates the sequence in n time. Multiplying these, we get an overall time complexity of n squared, n, which simplifies to n cubed. Shifting to space complexity, the helper function itself does not use any additional data structures. It relies on integer variables like first, second, and next_number, as well as string slicing operations for validation. These variables require constant space, amounting to 1 auxiliary space. Furthermore, string slicing operations, such as number I and number ij, do not create new copies but rather reference parts of the original string. Integer conversion during validation also scales dynamically in Python, so it consumes constant space. This efficient use of memory keeps the space complexity low. Considering the overall space complexity, the algorithm does not rely on any extra data structures aside from a few variables. Hence, the total space complexity is 1. Let's now examine the best, average, and worst case scenarios. The best case occurs when a valid additive sequence is found early in the loops. For example, if the sequence is identified quickly with smaller I and j values, the helper function can terminate early, reducing the number of iterations. In such scenarios, the time complexity can approach n squared. Conversely, the worst-case scenario arises when no valid additive sequence exists in the input string number. Here, the algorithm exhaustively tries all pairs, I, j, and validates the entire string for each pair, resulting in the full n cubed time complexity. These two extremes help frame the range of performance. For the average case, the algorithm generally terminates after exploring a fraction of all possible I, j pairs and validating partial sequences. Despite this, the asymptotic time complexity still remains n cubed, because the worst-case behavior dominates the scaling. Comparing this solution to a brute force approach highlights the optimization. A naive brute force method would involve generating all possible combinations of numbers in the sequence and verifying if they form a valid additive sequence. This would involve exploring every possible way to split the string into parts, leading to an exponential complexity of O(2 to the power of n). In contrast, the current solution drastically optimizes this by focusing solely on pairs of initial numbers, I, j, and validating the sequence in linear time for each pair. This improvement reduces the complexity to the polynomial O(n cubed), which is far more efficient than brute force. Finally, let's solidify the time complexity with a mathematical explanation. The outer loops together contribute O(n squared) iterations as they explore all valid pairs, I, j. For each pair, the helper function performs at most O(n) operations to validate the additive sequence. Multiplying these contributions gives a total complexity of O(n squared) (O(n), which simplifies to O(n cubed). Meanwhile, the space complexity remains constant at O(1), as the algorithm uses only a small number of variables and no additional data structures. By combining these insights, we see that the solution strikes a balance between efficiency and simplicity, effectively solving the problem within polynomial time and minimal space usage. When working with additive numbers, there are several common mistakes to watch out for. First, failing to handle leading zeros correctly can cause issues. Numbers like 1 foot or 001 are invalid unless the entire number is 0. This happens because substrings starting with 0 should only represent the value 0, otherwise, your splits and sequences will be invalid. Another frequent pitfall is integer overflow during concatenation checks. In languages like Java, summing integers that exceed the range of int can cause overflow, resulting in incorrect calculations. Using a larger data type like long or leveraging strings for computations can help avoid this. Additionally, skipping edge cases is a major issue. For example, strings that are too short or sequences that start correctly but fail to continue can lead to false positives or negatives. Lastly, inefficient backtracking implementations can create significant performance issues. If nested loops or recursion aren't optimized with proper pruning, the solution can become computationally expensive, particularly with long input strings. These are all important mistakes to address when designing your solution. Another common variation to avoid is assuming the additive sequence always begins with fixed lengths for the first two numbers. Restricting the starting lengths without exploring all possibilities limits the correctness of your solution, as the sequence can start with varying lengths. To improve your approach, focus on key patterns. An additive sequence follows the Fibonacci-like property where the third number equals the sum of the first two. Use this property to validate the sequence at every step. The starting point is critical. Splitting the string into two initial numbers of varying lengths determines the sequence's validity. It's also crucial to prepare for edge cases, such as strings like 112,358, 199100199, and those with leading zeros. Lastly, be mindful of time complexity. A brute force approach, which involves exploring all combinations, can be O(n cubed) due to nested loops. However, you can optimize the runtime by pruning unnecessary branches during backtracking. The concepts behind additive numbers are closely tied to several related problems. For example, LeetCode number 93, Restore IP Addresses, involves a similar backtracking approach to form valid IPs. LeetCode number 842, Split Array into Fibonacci Sequence, directly extends the additive numbers concept. LeetCode number 43, Multiply Strings, also requires string manipulation and arithmetic. Of course, the techniques you're practicing here apply directly to LeetCode number 306, the current problem. When considering alternative approaches, you have a few options. A brute force backtracking method tries every possible split for the first two numbers and validates the sequence. While simple to implement, this is inefficient for long strings. Optimized backtracking with early pruning can improve performance by stopping recursion when a sequence breaks or exceeds the input length. This approach is more efficient but requires careful pruning logic. Lastly, an iterative approach using two pointers can simulate the first two numbers and validate the sequence without recursion. While iterative methods avoid the overhead of recursion, they may be harder to implement cleanly. Each approach has its trade-offs, so choose the one that best fits your problem constraints and style. Great work! In conclusion, we've tackled the additive number problem by breaking it into manageable steps and leveraging string manipulation and backtracking. Remember to practice similar problems to strengthen your grasp of sequence validation techniques. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!